Sorry, like I was saying, it's rough to give the examples that are only right down the middle because it ends up not really showing too much about them, except the fact that they do really have line symmetry. Now, I can't seem to go this color. It seems to disappear right when I'm trying to get to it. There we go. I'll go ahead and do that. Okay, so just like this here, it goes right down the middle, and I apologize for not making perfect lines. Pepsi, right here, what does it have? Well, this does not have line symmetry. I can't cut this right down the middle and say this one side's a reflection of the other side. This is not a reflection. Neither is this right here. Of course, I can't do lines perfectly these days, but that's not a reflection either. In fact, none of these are reflections, but this one has rotational symmetry. If I take, I'm sorry, all these are paired together, but imagine me taking this circle and flipping it around. What would I have? I'd end up having the blue shape up here and the red shape down here. Now, technically, by design, if this is black and white, like you'll see on your page, it'll probably look like it has rotational symmetry 180 degrees, which means it has point symmetry. And in fact, I think that's the take-home thing that I'd want to say is if this were a black and white image, it would have rotational symmetry. But I'd have to rotate it all the way 360 degrees to end up with this shape again. The Audi, again, I can't rotate these images one by one because they're all grouped together. But if I rotate this 180 degrees, I'd end up having point symmetry about the central point. So just about right there. Now the question is, does it have line symmetry? The answer would normally be yes, but in this particular example, take a look, a very close look, at the way the chain link is. So maybe there will be a trick question here and there. But look at how the chain link is designed. This one overlaps right here. For this to have reflectional symmetry across this chain would need to overlap in the same vein right here. But it doesn't. In this case, it overlaps this way. So because of that, this is not a direct mirror image. It's actually very close to it, but it is not. Let's see if it works the same way the other way. If I go right down this line right here, keep in mind the chain links. See how this chain link works here. If I reflect it across, that means this chain link over here should be overlapping just like that, but it does not. So this does not have line symmetry. It's extremely close, but it doesn't. All it has is rotational symmetry, 180 degrees, which means it has point symmetry. Now the VW symbol, Volkswagen, right down the middle. This C actually has a couple, which is a good example here. Or I'm actually not sure what this is for. It could be Coach. I don't really know my brands too much. But it has one here. It has one across here, if I get it perfectly. It'd be better if I just move the line and not the entire configuration of this. And does it go across here, and does it have line symmetry? No, absolutely not. So here are the two aspects of line symmetry. And rotational symmetry, it goes 180 degrees. If I go 180 degrees, I end up with the same shape. So same thing, C and C. Now this Honda symbol looks like it kind of extends out this way and that way. So I can't cut across here and say that it has line symmetry. I'm sorry, I should go right across the H here. So that's not exactly symmetrical, but right down the middle it is. So I'll be okay that way. Also line symmetry. And no rotational symmetry either. Like I said, if I rotate this 180 degrees, then I have this big arching H down on the bottom, and that's not the same thing as this stubby little H. And what is this, Toyota? Toyota, Dodge, something like that. I think it's Toyota. I think the Dodge is a Ram. If I take this line here and try and make it more perfect, which it seems like it can't, then this also has line symmetry right there. So a lot of examples of line symmetry right down the middle in brands and logos. This is where you can see them in real life. Finally, graphs with symmetry, and I won't end up doing all of these, but I'll end up drawing the graphs, and maybe you'll have to look back later and say, okay, how are these done? Y equals X, I'll do with this pink line here. Y equals X looks like this, and you have to say, how can I make this line symmetrical? Well, as long as I make a line called called y equals negative x anywhere along here, and it goes perpendicularly to it, I've created a line of symmetry. Because these lines go infinitely in this direction and that direction, it doesn't have to go right across there. It could go just anywhere along here and just say all of these are different lines of symmetry for this one particular line. Okay, y equals x squared. Now, if you don't know how to graph this yet, go ahead and try an xy table, where x is your independent variable and y is your dependent variable. So I can plug in values for x. I'll do the standard negatives and positives here. Negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 2. So I'll take this red point here and plug those in. Negative 2, 4, that point goes right here. Negative 1, 1, 0, 0, 1, 1, and 2, 2. So y equals x squared is what's called a parabola, if you have not been familiar with those yet, and that's not perfect, but it's basically a U shape that goes up and down. And where is its line of symmetry? So that's what you have to kind of figure out here. It ends up being this, which will cut it in half. And that line is called, anyone? Bueller? Anyone? X equals 0. So that's its line of symmetry for that particular graph. X equals y squared is kind of the same thing, only it's flipped a little to the right, where now I'll have a independent variable y and a dependent variable x. So we'll do the exact opposite here. If I take y and x, I'll make another table. This time I'll plug in values for y and get values out for x. You end up getting the same things. Negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. But now x is 4, y is negative 2. So now it looks like it's going this way. Like so. So make sure you check those points and say those are accurate. And it ends up being a parabola shaped this way, which is not a function, by the way, but it is still a graph. So how can I divide that? Like that. That's its line of symmetry, which is, anyone? Bueller. Y equals 0. So that's its line of symmetry, which divides that line evenly. X squared plus y squared equals 16. That is the graph of a circle, whose center is at 0, 0, because there's no h or no k, and its radius is 4. So I'll just go ahead and graph that one quickly. Starting at 0, 0, I'll go 4 up, 4 over, 4 down, and 4 over on the other side. And you would end up making a circle out of that. I'll just go ahead and go the shortcut way and just make a circle myself like that. And as we know, a circle has line symmetry everywhere. It also has rotational symmetry everywhere. What if I just took this circle and just started rotating it? Anywhere I rotate this, I end up with the same exact circle. Doesn't matter how much. So it has infinite amount of lines of symmetry, infinite amount of rotations of symmetry. So there's my circle, which has an infinite amount, like I said. So you can divide them anywhere as long as they go through the center. I'm sorry, as long as it goes about 0, 0. So any line and any rotation. Y equals x cubed, same thing. Make an xy graph. So I go xy with the t-chart here, and I go negative 2, negative 1, 0, 1, and 2. You have to know what x cubed is. Negative 2 cubed is negative 8. Negative 1 cubed is negative 1. 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. So I graph it like so. It looks like I didn't go all the way down here, but I'll make these values work like this and plot them on, and you end up getting kind of a snake-like shape like this, which goes down. This does not look to have any sort of line symmetry. If I go through like this, it doesn't seem to cut across exactly so or anything like that. No mirror images. But rotationally speaking, if I take this and rotate it about here 180 degrees, I end up getting the same shape on the other end. So it has point symmetry. And finally, y equals absolute value of x. I don't think I'll have enough time to show the actual graph, but that means for any value of x I put in, like all these, the y just ends up being the positive value. So 2, 1, 0, 1, and 2. So it looks like that, which ends up being a V shape here and here. And it has line symmetry going across, again, x equals 0. So in summary, if you're watching this at home, I want you to see what objects in your house have reflectional symmetry or rotational symmetry. And here's the homework for tonight. And I recorded, over the weekend, I recorded some solutions to some textbook problems, which you can see. Most of the problems are not homework examples that you used, but at least you'll be able to get an example of some of the more challenging problems and things that you can work